This is lecture number 18, and this is a continuation of chapter 7, and we know that we are discussing about the Q switches, and here we are going to discuss about the first kind of Q switch, that is electro-optic type. Electro-optic modulators. This is first kind of modulator we are going to study here, and this modulators actually is based upon the phenomena of Birefringence, which is induced or introduced in the crystal, because of the electric field. Birefringence actually is a certain kind of property of a certain crystals that they show the double refraction phenomena. And this refraction is depending on the polarization. Okay, so the most common one, the crystal which is used for this kind of phenomena to study or to introduce, or in the electro-optic modulator, that is calcite. So calcite is a naturally existing crystal having this kind of properties. What it does actually, you can also see in the figure here, it separates the beam. Okay, and both the beams are reflected, but both the beams having different polarization. Perpendicular components and the parallel components, you can clearly see here. So basically, birefringence is a phenomena where the light is refracted into two. Okay, and that is why it's also called the double refraction. And both the refracted rays having different polarization. Okay, so make use of this phenomena. They make actually electro-optic modulators. So the high electric field is applied along the crystals, along the parallel axis of the crystal, and then we can use as a switch on the basis of polarization. So first thing, what is mentioned here is a birefringence. Birefringence, as I explained to you, what is birefringence? Okay, and is also written here. You can see in which the incident ray separates into two rays that travel in different directions depending on the polarization. Okay, so basically these crystals, they are having two refractive indexes, and refractive index, you know already, first time is the mathematical explanation given by the Snell. And so refractive index for the plane, parallel components, and refractive index for the perpendicular components. So in case of a calcite, you can see the index of refraction is 1.6 for a light in a perpendicular plane and 1.49 for light in a parallel plane. So if the refractive index is different, definitely the rays will be traveling a bit far from each other after passing through the crystal. In the normal case, there is only one refracted ray, but in this case there are two refracted rays and having different polarization. And this is definitely it's a property of this kind of naturally existing crystal calcite. Now they are also fabricating different kind of crystals to have this kind of properties, and to apply the electric field, uh, to apply the high electric field is also one of the important thing, because without the application of high electric field, it not work. So what you see here, the incident beam, and then it's refracted, and you have two beams with different polarizations. तो क्या होता है इस तरह क्रिस्टल के बायरफ्रिंजेंस क्रिस्टल में कि आपकी लाइट आई, और लाइट आने के बाद जब ये क्रिस्टल बायफ्रिंजेंट जो क्रिस्टल है इसमें से पास हुई, तो उसके पास होने के बाद इसमें आपके पास पैरेलल कंपोनेंट्स आ गए और कुछ परपेंडिकुलर कंपोनेंट्स आ गए, तो आपके पास दो रेज आ गई हैविंग डिफरेंट रिफ्रैक्टिव इंडेक्स। ठीक है, एक 1.66 है और एक 1.49 रिफ्रैक्टिव इंडेक्स है। सो वी कैन इजीली सेपरेट दीज टू रेज, हम बड़े आसानी से इन दोनों को सेपरेट कर सकते हैं और इसी बेसिस पे ये इलेक्ट्रो ऑप्टिक मॉड्यूलेटर जो है ये काम करते हैं। जो क्रिस्टल इसके लिए यूज होता है वो कैल्साइट क्रिस्टल है, जो कि नेचुरली हैविंग इस तरह की प्रॉपर्टीज के होती हैं उसमें। On this slide, this figure, what you see here is very important. Okay, we have this electro-optic cell which contain the kind of gasket kind of enclosure, and it has a crystal inside and electric field arrangement on the both sides of the crystal. So what exactly is happening here when we apply the electric field? When we apply the electric field, then definitely the birefringence phenomenon comes in action. Okay, so if we don't apply, then there is nothing, no change, so light is just passed through like a normal way. So basically this phenomena is important, but it needs a high electric field along the axis of the crystal. What is, now let's go through here. So say this phenomena is used in the case of Q switch to block an intracavity light beam. Block means if you change the polarization, the incoming light. So what exactly happening here? Incident light is polarized and then pass through the electro-optic material. This is polarizer and this one is also polarizer, and both have different polarization. Okay, maybe parallel one, perpendicular other, or perpendicular first or parallel other. Okay, so when the incident light passed through this polarizer, it polarized. Okay, and after polarized, this polarized beam passed through the crystal. But if the light is already polarized, then we don't need this arrangement. Okay. Now, light exiting the crystal is passed through a second polarizer filter called an analyzer. After passing through this cell, electro-optic cell, it passed through the analyzer. Okay. Now, important thing, since the crystal causes no change to a light pass through it when no energized, where there is no electric field, so the light will pass through like as it is. Okay. Analyzer, what it does? This is analyzer. Oriented at 90 degrees to the polarizer. Okay. This polarizer and this analyzer, as I told you, they have the 90 degrees difference, orientation difference. Okay. So prevents any light from being transmitted through the device. Any light from being transmitted through the device. So what is explained here? You can try to understand that once the light is here, it passed through, electric field is off. In this case, this analyzer is 90 degrees of this one. Okay, it will not let the pass it will not let the light to pass through. Okay, not this crystal, this analyzer, when there is no electric field. So that is why the light is not passing through. So it acts as a shutter, which acts as a shutter. So when you apply an electric field, external electric field, so the direction of the polarization of light passing through it is rotated 90 degrees. When you apply the electric field, you know the Birefringence phenomena come in action. So when it comes in action, so what happened? You have the two polarizations, okay? So definitely what it does, the direction of the polarization through it's rotated by 90 degrees. So it will rotate, the light will rotate the 90 degrees. When the light will rotate 90 degrees, definitely then this analyzer will not stop this light, and light will pass through. Now the shutter is open. So now if I try to explain in Urdu, क्या होता है कि ये आपके पास क्रिस्टल है और इस क्रिस्टल को अटैच किया गया है इलेक्ट्रिक फील्ड के साथ. एक ये आपका पोलराइजिंग फिल्टर है, एक ये आपका पोलराइजिंग फिल्टर है. इन दोनों की ओरिएंटेशन जो है ना वो 90 डिग्री का डिफरेंस है दोनों में. ठीक है, पहले जब लाइट आती है, जब लाइट इसमें से पास हो जाती है, अगर तो लाइट अनपोलराइज्ड है तो पोलराइज्ड हो जाएगी इस पोलराइज में पास करने की. इलेक्ट्रिक फील्ड नहीं अप्लाई की, वो एज इट इज इसमें से पास हो जाएगी, लेकिन वो पोलराइजेशन है यहाँ से ब्लॉक हो जाएगी क्योंकि इसकी ओरिएंटेशन वो है 90 डिग्री देन द फर्स्ट वन. तो ये एक्ट करेगा एज ए क्लोज शटर. ठीक है, अब अगर हम इलेक्ट्रिक फील्ड ओपन कर देते हैं तो इलेक्ट्रिक फील्ड ओपन करने से ये क्या होगा कि इलेक्ट्रिक फील्ड बायरफ्रिंजेंस जो आपका फिनोमेना है वो एक्शन में आएगा. तो वो एक्शन में आएगा तो वो रोटेट कर देगा लाइट की पोलराइजेशन. वो लाइट की पोलराइजेशन जब रोटेट कर देगा तो ये एनालाइजर उस पोलराइजेशन को स्टॉप नहीं करेगा, लाइट इसमें से पास हो जाएगी. ठीक है, दिस इज द सिंपल वे हाउ यू कैन एक्सप्लेन दिस थिंग. और एक बात और ध्यान में रखें कि अगर लाइट ऑलरेडी पोलराइजर, यू डोंट नीड, हमें नहीं जरूरत इस पोलराइजर की. फिर इफ लाइट इज नॉट पोलराइज देन वी नीड इट. ओके, सो ये जो फिनोमेना है, ये इलेक्ट्रो ऑप्टिक जो डिवाइसेस हैं जिनमें कैल्साइट क्रिस्टल यूज होता है वो इस तरह काम करती है. Now let's move to the next slide. There are two kinds of electro-optic effects. Two kinds of electro-optic effects, and both, I mean, refractive index is changed relative to the applied electric field. How much electric field we applied. There is a certain range, okay? The two phenomena are called focal cell effect and Kerr effect. It depends materials. For a Kerr effect, different materials are used. For focal cell effect, different materials are used. And both these phenomena can be used in electro-optic devices. Definitely we have to use a crystal who is exhibiting this kind of properties, double refraction or something like this. The most common and most famous principle or the effect is Pokel's effect. It's called Pokel cell, which we have seen in the last slide. Pokel was one of the scientists actually who worked on it, and then Pokel cell. This device is available in the market. It's a very expensive device and entirely based on Pokel's effect. And Pokel's effect is using the same kind of birefringent crystals and have double refraction. So what is written here now? The Pokel cell change in refractive index is a linear function of applied electric field. When you apply the electric field, refractive index change. So it's a linear function. Linear, okay, change in refractive index is linear with the electric field. Okay, like this, if you draw this equation, delta n refractive index, A is any coefficient, which is called the electro-optic coefficient, and E is the electric field. And this electro-optic coefficient, it depends on the property of the material. And definitely it is 0 when the material is non-crystalline. It has to be in the crystal. Okay. And there are two specific crystals are used in electro-optic modulators, which are fabricated definitely in the labs or in the optical industries. First one is ammonium dihydrogen phosphate. It's called ADP. Ammonium, you can say dihydrogen or dihydrogen phosphate. Second one, potassium dihydrogen phosphate, KDP. This is more famous, KDP crystal. ADP and KDP. And third one is lithium niobate. Lithium niobate is a less common, mostly KDP is used, and they have a different refractive index. It means they are showing the birefringence properties, phenomena, okay? And birefringence means they have the different refractive index, one for the parallel polarization, other one for the perpendicular polarization. So like in case of ammonium hydrogen phosphate ADP 1.51, 1.47, and KDP 1.51, 1.47 is almost same. And in case of lithium, you have 2.23 and 2.16. So these are the material, these are the crystals which are used in a Pockels effect. Okay, for the Kerr effect, different materials are used actually, and as I mentioned, that's more common and popular is the Pockels effect in electro-optic devices. Here, little bit about the other electro-optic effect, which is called the Kerr effect. Kerr effect is very important actually in when we study the femtocycle laser, but in other applications also, and there is a research actually, many people they do research and still going on to study the Kerr effect. Pockels cells effect is somehow understood now, where Kerr effect study still going on. And definitely change in refractive index when we apply the electric field, but for this kind of effect we need a very high electric field. Very high electric field, like you can see here, it's E2 square electric field. So what electric field we are using in the Pockels effect, we need it twice here. Okay, so it's also hell of job to make such kind of system, such kind of electronic circuit to give electric field, this much electric field, and to not damage the crystal. So refractive index is equal to A2E square, where A2 is definitely the electro-optic coefficient, is second order electro-optic coefficient. Previous was the first order electro-optic coefficient. Or this second order electro-optic coefficient, more generally we can also write like this, like here. So lambda K. This K is a Kerr coefficient and lambda is a wavelength, definitely. So the above, this equation will be of this form if you substitute this value, okay? And so it means it's depending on Kerr coefficient and wavelength, the property of particular materials, okay? It is studied somehow that there are many materials they exhibit or they show this kind of effect, care effect. In some is a small care effect, in some of the more prominent care effect. So some people say almost all the materials they can have a care effect. Some is very small, which we cannot measure, and some they are more prominent, which we can be measured. But in any case, we need high electric field to observe this kind of effects. And the common type of material which is used for the care type AO modulators is liquid nitrobenzene. And liquid nitrobenzene is a toxic, it's a liquid. You need a special kind of cuvette for this one to fill it up. And then you apply the electric field, which is not very much practical. It's a liquid, but it's kind of gas as well. Okay, and it's toxic. It's difficult to handle. So that is why, I mean, care effect is observed in, but it's not as fruitful in electro-optic switching. So that is why Pockels effect is more common in electro-optic switching. Care effect is studied in some other things and used in other things. Here, once again, you can see the same figure here. A little more explanation about the electro-optic modulators. Especially when we use the crystal ADP and KDP, this is related to pocket cell. So it is sandwiched here, definitely the electric field electrodes are here and the crystal is sandwiched. And here they have explained actually like how it is made and somehow how it will work. So what exactly the crystal is then inserted between a pair of crossed polarizing filters. These are two crossed polarizing filters, this one and this one. Okay, so cross polarizing. So here it's inserted and this sandwich between certain arrangement so that electric field can be applied. Okay, and that will be a direct current DC. Potential of several thousands of volts, kV range, okay, DC, volt in kV range, and that has to be in the parallel to the optical axis of the crystal. Optical axis of the crystal. If this is your crystal, the optical axis is this one. So, okay, so the electric field is also applied in this direction. Okay. So what happened? The refraction of the crystal changes. When the refraction is changes, then it divided into two polarizations, perpendicular, parallel, and according to that it passed through the analyzer, as I explained before. So electric field here, volt per meter, you know already, is a unit of electric field. So how it is applied? The electric field applied on the both sides of the crystal. Thickness. So it is the thickness of the cell, and which is obviously the distance over which the electric field is applied. If this is your crystal here, sorry, if this is your crystal here, you apply the electric field here, here. Okay, if you apply the electric field here, so this will be the distance. Okay, so electric field V over M, volt per meter. So this is the distance over which you are applying the electric field. This is how it works. इसके दरमियान ये क्रिस्टल रखा है, क्रिस्टल के बाद ये दो पोलराइजर हैं, ठीक है, 90 डिग्री ओरिएंटेशन पे. इलेक्ट्रिक फील्ड जब हम अप्लाई करते हैं, हमें पता है कि इलेक्ट्रिक फील्ड वोल्ट पर मीटर है. तो इसके अक्रॉस जब हम अप्लाई फील्ड करते हैं तो ये लेंथ जो है क्रिस्टल की, जिसे थिकनेस कहा गया है, थिकनेस जो है क्रिस्टल की, ये उसका डिस्टेंस है जिसमें एक इलेक्ट्रिक फील्ड ट्रेवल करती है. सो दैट इज वाई I mean electric field we have the unit V over M. So डिस्टेंस यहाँ पे जो है वो एक क्रिस्टल की एक साइड से दूसरी साइड का है। Here, what do you see on this slide? The phase change of light passing through a modulator. Light phase of the light is changed, okay, passing through a modulator. Is proportional to what? Is proportional to the thickness of the electro-optic material, the crystal which you are using. Okay, like here is written. Along with this one, refractive index is also changed because of the electric field. Okay, so mathematically we can write like this: this delta phi is a phase change is equal to 2 pi delta n L over lambda. Okay, 2 pi cycle. Okay, and delta n is the refractive index, L is the thickness or the length. Okay, and lambda is a wavelength. So basically this phi, the phase, is directly proportional to L and inversely proportional to lambda. Now if we write the equation in terms of like a transmission, like here, so transmission is changing according to the change in refractive index in the crystal. Okay, the refractive index changing, transmission is changing. So here what you see, this is a transmission and T naught is maximum transmission, and here the same thing what you have observed of pi delta n L over 2 pi. So delta n is the difference in a refractive index. Okay, refractive index or difference in a refractive index for two polarizers or polarizations. L is the length of the crystal and lambda wavelength of the crystal. We have this equation for the phase, this equation for the transmission. Okay, when we study the transmission of the wave. Now the last line, if you see here, the birefringence is a function of applied electric field and hence the voltage applied to the crystal. The birefringence is a function of applied electric field. Definitely you apply the electric field, then this phenomena you can observe, and hence the voltage applied to the crystal. So whatever voltage we apply to the crystal, it is for the electric field, to generate the electric field. Okay, so definitely the birefringence is a function of applied electric field and hence the voltage, so it's a function of voltage as well. When maximum transmission occurs, so maximum transmission occurs when maximum transmission occur so maximum transmission occurs when the term pi delta n L over pi is equal to pi by 2. Pi when the maximum transmission, we have to, we are thinking when maximum transmission is possible. Maximum transmission is possible if you substitute delta pi delta n L over pi is equal to pi by 2. How it comes pi by 2? If we have the change in refractive index is equal to lambda over 2L. Lambda over 2L. If you substitute this value, okay, 2L, then you get a pi by 2, which is the maximum transmission. So here, this delta n is equal to lambda by 2L. So change in refractive index is directly proportional to the wavelength and inversely proportional to the L, the thickness. Okay, so if we substitute this value here, then we get this one, okay, which is pi by 2. And at this condition, we will have maximum transmission through the crystal. One more thing, voltage, applied voltage. There's a word actually is used which is called the half wave voltage. Half wave, the voltage applied for the half of the wave. Okay, so that is why it's written V1 by 2. So half wave voltage is also a property of a materials itself, this kind of materials, okay. And this voltage, it depends wavelength. If the wavelength is increasing, then this half voltage will also be increasing. Okay. So like here it's mentioned V1 by 2, V1 by 2, and wavelength 1, wavelength 2 is equal to lambda 1, lambda 2. Half wave voltage increases with the wavelength. Okay. So electro-optic modulator operating in the infrared region, definitely its wavelength is higher. It's much higher voltage they need to introduce to satisfy the condition, okay, of birefringence. So electro-optical modulators, they need higher voltage, very high voltage, when they are operating in the infrared region. If not in infrared region, visible region, maybe they need less voltage. In the visible region, it will be like 5 to 10 kilovolt. So that is why if we are using carbon dioxide laser with 10.6 micrometer wavelength, then probably it's not good for us, or it's not a good choice to use electro-optical modulator. There are some other techniques, maybe acousto-optic, or maybe other one, to use as a switch. So this is the thing which is supposed to be considered. Birefringence phenomena is there, okay, and it only you can observe when you apply the high voltage. And if you apply the high voltage, then definitely you observe this phenomena. But for different, it depends on the different wavelengths. For different wavelengths, voltage has to be different. So for the infrared, the voltage will be higher. So no doubt, electro-optic switch is higher than the mechanical switch, faster than the mechanical switch, okay. And switching time is less than 10 nanosecond, which is very difficult in case of if you make a mechanical switch or with electronic or something like this. And electro-optic modulator is so fast that it is often used as a shutter for ultra-fast camera. Ultra-fast camera to observe or to capture the ultra-fast phenomena, like a photograph of atomic blast or something like this. This is ultra-fast cameras. But it's not like simple arrangement. You need ultra-fast ray of light for this kind of things to capture. At the end, this is a problem example you can also see in the book. At that problem, you have to do it by yourself. How did he perform in the book? Okay, it's a simple using the same equation which I have explained. Okay, thank you very much for this lecture.